Okay, so the plan today is to finish that one last problem in 7.8 improper integrals and to start on chapter 8, some applications of integration and probability. And today our goal is to get through 8.1 arc length. So that's the plan for today. Um, as just kind of a reminder, we wrapped up the kind of integration techniques module, if you want to call it that, from kind of the end of chapter 5 and the beginning, well, probably 2/3 or so of chapter 7. So the integration techniques worksheet is posted on Blackboard. There's a supplemental uh, recording, a supplemental YouTube video posted on YouTube. There's a um, so there's a supplemental videos folder for Calc 2 that's up there on the playlist. It's a different playlist than our normal videos where they're posted. So, but if you have any questions on the details of those integrals, let me know. There's also a couple integrals. I recorded that in a previous semester. There's a couple integrals that say like done in class. We kind of skipped over doing them in class. Um, so the couple that say done in class, we didn't do in class, but if you have questions on those ones, just pop in office hours or send me an email and I'm happy to elaborate. Or you can pull up the recording from the previous semester from spring of 2024 and see those examples completed. So whatever works best for you. Um, in chapter 8, this is the type of material where we can be pretty flexible. So we can cover this material in a bit more depth or a bit less depth, just depending on how time is progressing. So this is where I'll kind of, I'll take a look at the schedule, how things are progressing, and change the amount of material that we cover in chapter 8 on that basis. So things will be a little bit flexible in chapter 8, as these are really all applications. Personally, I really like probability theory, so we probably will cover probability theory. I think it's also really good to have seen the ideas once before you go into, say, an engineering stats course, or if you're doing an applied math track, something like a probability theory course. I think it's good to have at least seen it once before, see how everything relates to calculus, you know, just to give you that little bit of leg up on the technical side of things going into those courses. All right, the quote of the day for today, one quote and one kind of related quote is, I don't know why my window's a little skinnier. Then let me try to get this on one line there. There we go. All right. The quote of the day is, there are several variations of this, but basically, don't walk over dollars to pick up pennies. In other words, you have a limited amount of time, energy, cognition, money, whatever it may be, to spend. Um, and some people spend a lot of time and effort hyper optimizing low yield pieces of their life, their education, their career, whatever it may be. Uh, right. And then they leave the kind of higher yield uh, stuff to kind of fall apart. Uh, so in other words, don't like run all over town looking for sales on, some grocery item that's going to save you 50 cents, if that means that, you have less time to spend researching the car you're about to buy for $20,000, right? I'm much happier even paying double the price that I maybe could have paid for a grocery item that costs in absolute terms, $2 versus $1, than even overpaying by 1 or 2% on a $20,000 car, which is hundreds of dollars. So, uh, give some thought, and this obviously applies to education as well. You're being pulled a bunch of different ways by a bunch of different courses. Give some thought to which courses are most important for you to do really well in, to understand the material in. And I am fully aware that for some people, the answer might not be calculus 2, even though every instructor wants to believe that their course is the most important course, but we have to be realistic as well. Um, and in each course, what are the things that you're just going to let go, right? Maybe there's a problem on a homework set. If you get this problem correct, it'll get you, 7 points in homework, but that doesn't amount to very much at the end of the course. But if you spend 45 minutes or an hour working on that, and as a result aren't able to spend that 45 minutes or an hour studying for an exam, and if your grade on the exam goes down, 5 percentage points because of that, that's probably not a good trade-off. I mean, ideally, we want to work through hard problems because it's good practice, it's good mental practice, and it builds up the test taking skills for when we're on an exam and have to perform. But um, but there's always a balance there, right? So some people like really, really want to see exactly, 100% perfect score on all their homework. But if you're hyper optimizing that and as a result, not doing so great on the exams, that's not a good trade-off. If you're getting 100% on all your homeworks and doing great on the exams, hey, thumbs up, great job, right? I mean, as long as you're not like failing your chemistry course because of that, right? As long as something else isn't suffering. Um, and I think a related idea is this is often kind of attributed in some sense to Carl Jung, the psychiatrist from the early 1900s. Kind of Freud and Jung were kind of, you know, roughly ballpark same time and kind of played off of each other's ideas. Um, and I don't think he ever said or wrote this really. I mean, his writings were mostly in German, but I don't think he ever wrote something that was translated this way. But I think this is an idea that Jung would agree with or would have agreed with, and is often attributed to him. And it goes something like that: that which we need the most will be found where we least want to look. So I think one of the reasons we hyper focus on sometimes optimizing the or picking up the pennies, so to speak, hyper optimizing the easy stuff and walking over the dollars is a lot of times the highest yield stuff is the stuff that we don't want to do, right? It's kind of because it's the stuff we don't want to do, we push it off to the side and we get worse at it and we get better at everything else. And it's like this becomes my worst weakness, and it gets worse and worse because everything else is getting better because I'm working on it. But that thing that I avoid is the thing that where the highest yield might be able to be gained. Uh, play your life in a sense to your strengths, but also work on your weaknesses so that they're not such extreme weaknesses. All right, so looking at improper integrals, really quickly recall the previous definition when we were looking at improper integrals with an infinite domain of integration. So if we're examining, for instance, integral a to infinity f of x dx, we define that to be limit as t goes to infinity of the integral a to t f of x dx, provided the limit exists and is finite. Pretty analogous definition for part B. For part C, we could easily get tripped up here. We could easily think that integral minus infinity to infinity f of x dx, what we would do is do limit t goes to infinity of integral minus t to t f of x dx. But we noted last time that that's not really a great approach because we could set up kind of similar schemes in many, many different ways that all seem kind of equally valid or equally reasonable and get lots of different answers. So that wouldn't be a well-defined way to set this definition up. What we do instead is we pick a point C, a real number. We break this into two improper integrals, one that goes off to negative infinity, one that goes off to positive. And we say that this doubly infinite integral exists if and only if both of these integrals or both of these limits in these integrals exist and are finite. And in that case, it's the sum of those two integrals. When the limits exist and are finite, we call the integral convergent. And we say that it converges to the value of the appropriate limit or sum of the limits. And otherwise, if the limit doesn't exist, or if the limit exists but it's infinite, we say that the integral is divergent. Any questions on that from last time? I mentioned last time that once we start throwing around infinities, we have to be very definition dependent. We have to stick very carefully to exactly what the definitions say. So it's important to understand and to know what these definitions say. We don't want to be flippant at all here because it's very easy to make a misstep and come up with a completely different answer. This also goes for infinite series, which we'll talk about near the end of the course in chapter 11. Same thing there, same caution. And that's really where students get tripped up a lot is they get a little hand wavy with the definitions. And once we start throwing around infinities, it's really easy to be led astray. So we want to be very careful to stick to the definitions. Okay, we mentioned there is also another type of improper integral. So we can have an area that instead of roughly speaking being infinitely wide is kind of infinitely tall. We can have a vertical asymptote. So if I was looking at integral 0 to 1 f of x dx, oh, wrong one, this. It seems like as x goes to 0 from above, f of x goes to positive infinity. And at first glance, this looks very different from our previous situation, except that we realize that if we just kind of flip this over the line y equals x, it actually kind of actually looks a lot like the previous situation. So we have this vertical asymptote here, and in the previous setup, we kind of said our heuristic was, well, if the heights of the different chunks of area as we go out to say the right, for instance, and this an example like this one, if they get small, but not just that, if they get small enough fast enough, then we can have a limit that converges. We can add up infinitely many positive chunks of area and have it come out to a finite number. If they don't get small, or maybe they get small, but they don't get small particularly quickly, then maybe we add them up and they add up to an infinite area. We had a p integral that we talked about last time that, for instance, integral 1 to infinity of 1 over x dx does not converge, but 1 over x squared does converge. P strictly bigger than 1, that power in the x in the denominator is what leads to convergence. So can we imagine a situation kind of similar here? If my, roughly speaking, if I was to look this way, which is not how Riemann integration works, but just kind of heuristically, just getting a feel for this, can I say that if my areas get kind of skinny enough, fast enough as I go up, that maybe I have a finite area here? That kind of makes sense to say based on what we've seen before. But again, this is kind of heuristic, hand wavy, gut feeling kind of stuff. We need to make precise what we're talking about here. We have the feeling that, we could have vertical asymptote type domains that could result in a convergent integral. Let's say exactly what we mean by that. So these are our definitions. Convergence of an improper integral with a discontinuous integrand in the sense that we're looking at a vertical asymptote. So here, if I look at the integral from a to b, if f is continuous on closed a to open b, then I can define integral a to b f of x dx as limit as t goes to b from below, integral a to t f of x dx. Again, provided the limit exists and is finite. So if I have a discontinuity at b, right, note that the continuity is only guaranteed on closed a to open b. If I have a discontinuity at b, if I have a vertical asymptote at b, this is the limit I want to evaluate to see if my integral converges. Similarly, if I have a discontinuity at a, if f is continuous on open a to closed b, we do the analogous thing. We approach a from above. We take that limit as of integral t to b f of x dx. So we're sticking within the integral, or within the interval where we know the thing is convergent and kind of, limiting ourselves out to the whole interval of integration. If that limiting process, if that limit exists and is finite, if that limiting process works out nicely, then our integral converges and we can say that that's its value. If not, then our integral diverges. And lastly, what if f is discontinuous at C, a point in closed A to B, but is continuous otherwise? Well, then we break the interval at C, kind of analogous to what we did up here. We break the integral at C, and we look at integral A to C, f of x dx, which is continuous on closed A to open C. Evaluate that using part A, and we look at integral C to B, f of x dx, which is continuous on open C to closed B. We evaluate that this way. And if both of those limits exist and are finite, then this integral converges and its value is the sum of those integrals. So it's a pretty analogous way of looking at this, or a pretty analogous way of setting up our definitions to the kind of horizontally infinite domain. But there are a couple of nuances here. So let's take a look at this example. Integral 0 to 1 of 1 over cube root of x dx. I know that 1 over cube root of x, well, that is just x to the minus 1/3 power. That's a power function. It's continuous on R except at 0. So my point of discontinuity is just at 0. Everything else on the interval from 0 to 1, I'm continuous at every other point. So I'm continuous on open 0 to closed 1. So that looks like part B for my definition up here. So I want to examine what happens to integral t to b, f of x dx, where t is a number between 0 and 1, strictly bigger than 0, and then take the limit as t goes to 0 from above and see what happens there. So let t be in open 0 to closed 1. Since we're taking the limit as t goes to 0 from above, we certainly see that t is going to be bigger than 0, not equal to 0, and we can certainly keep it below 1. There's not a problem there. So what's integral t to 1 of, and we'll choose to write this as x to the minus 1/3 dx. Well, this is a power function. I add 1 to the power, that gives me x to the 2/3. Divide by the power, which gives me a 3/2, and evaluate from t to 1. Or this is 3/2 times 1 to the 2/3 is 1 minus t to the 2/3. So that's what this integral here is. Then I want to look at what happens to the limit as t goes to 0 from above. Now, t to the positive 2/3 power, this is just like the cube root of t squared in the numerator. So it's, just to make that very clear, I just put it over 1 for no real reason other than just to really stress that it's in the numerator. As t goes to 0 from above, there's no problem at all here. this just goes to 0. Right? The integral kind of, in a sense, pulled that power, that x mass into the numerator, and now when we evaluate at t, let t go to 0, no problem. So this is just 3/2. This integral, or this limit, does converge. It is finite. So this integral can be said to be equal to this limit. This integral converges and is equal to the value 3/2. Even though it has this asymptote at 0, right? And I'm looking at this area. So it's kind of an infinitely tall area. Goes up forever. But it does get, in some sense, skinny enough, fast enough that it does converge to, in this case, 3/2. So an interesting exercise. I think it might be a homework problem as well. Consider integral 0 to 1 over x to the p dx. Converges for what values of p? This will look quite similar to the integral 1 to infinity 1 over x to the p dx problem we did before. Okay. Any questions on improper integrals? As a little side note, people often say that Calc 2 is actually the hardest of the 3 calcs, even harder than Calc 3. Calc 3, a lot of it is just kind of doing Calc 1 3 times sequentially. But I think Calc 1 and Calc 3, the definitions and the things that we're doing and the calculations we're doing just feel a lot more natural. There's a lot more kind of intuition that we can say, yeah, this feels like the right thing to do. In Calc 2, we have a lot of these situations like improper integrals where what feels like the right thing to do might not be the right thing. We're much more reliant on definitions. So some of these integration bits, some of the stuff a bit later on sequences and series, again, a little more abstract. It's a little more definition heavy. We need to stick closely to the definitions because of that. So we need to just be a little bit more careful with the details in Calc 2. And to be fair, Calc 2 just has kind of a lot of material, and it's kind of a motley assortment of topics. So that's a little bit true of Calc 3, but I don't think so much as Calc 2. Okay, so kind of speaking of motley assortment of topics, we are now going to move into Chapter 8 on applications and start our first application at 8.1 arc length. Okay, so what is arc length? It's the length of a curve from one point, AF of A, to another point, BF of B, importantly measured along the curve. So I imagine I have two inputs, A and B, and two outputs. Here are points A, F of A, and B, F of B. And I have some curve connecting them. And kind of my question here is, if I'm like standing over here with one of those little, you ever see the guys that like measure distances outside? They have like a little roller thing that they roll on the ground and it measures the distance, because your little 25-foot tape measure only goes 25 feet. So if they want to measure hundreds of feet, they have a little roller thing that accumulates the distance. So imagine you're standing here and you're going to walk along this curve from AF of A to BF of B. how much distance would you measure? How many steps would you need to take in a sense? It's not going to be the same as if there was just a straight line going there. And it's not going to be the same as if, this was even hillier. Or another way to look at it is like, if I want to draw a line from AF of A to BF of B, like how much ink am I going to use, right? I'm going to use more ink drawing this line than a straight line, but less than one that had even a bigger peak and a bigger valley. Okay, so how can I approach this problem? Well, one thing that we've seen so far in Calc 2 a couple of times is when we have a continuous problem like this, like a curvy problem, often what we'll do is we'll look at a small chunk, we'll take a really small interval to consider. We'll say on this small interval, can I get an approximation that's not a curve, that's just like a constant or something like that, that's just maybe a straight line, use that approximation on a small interval, accumulate those approximations, add those approximations up over the entire uh, spectrum of the problem, get an estimate for the answer, and then take a limit as my interval size goes to 0 and number of intervals goes to infinity. And our strategy here is going to be exactly the same. We're going to take a look at, say, some small window. Say delta x. And let's come over here. This window has width delta x. And I want to know what the length of this curve is from this left endpoint to this right endpoint of this small window. So delta x, and we're thinking of this as being small. Well, on this small window, f of x, the black curve here, is approximately the same as L of x, the linear approximation to this function, just connecting these 2 points with a straight line. Or if I look at connecting these 2 points with a straight line, I can see that I have a triangle here. Maybe it doesn't look like such a nice triangle the way that I drew it, but we can imagine a triangle. Here I have a little chunk of length. Maybe I'll call this L sub I. This will be like the ith interval. So maybe I'll call it L subscript I to indicate the ith interval. I have a right triangle. It has base width delta x, thinking of that as being a small number, and it has height, let's call it delta y. And I see by my Pythagorean identity that Li squared equals delta x squared plus delta y squared. And again, L sub I should be approximately the length of this curve f of x, which I've kind of drawn very exaggerated up here, so you can see the difference. Should be approximately that length when delta x is small. So then what is Li? Well, missed my delta there. And if I factor a delta x out, I factor a delta x squared out of the delta x squared plus delta y squared inside of the square root, and it comes out as a delta x outside of the square root. And that's what I have. That's my Li. As a little side note, delta x will just suppose it's going to be the same for all of the intervals, but delta y would really be kind of a delta y sub I. The change in the height is going to be different on each interval. So this would be for the ith interval. So this really should be delta yi, but I'm not being super careful to write that. But I look at delta y over delta x. If delta x is small, that should be well approximated by, say, f prime at xi, right? So this is kind of like f prime at x sub I. Or my overall arc length is approximately the sum of the LIs, or the sum of the square root of 1 plus delta y over delta x squared, delta x, just adding up the approximate lengths from each of these bunch of different windows going from A to B. And then what I can do is I can let n go to infinity, the number of intervals go to infinity, and delta x go to 0. And this turns into an integral from A to B, square root of 1 plus, and delta y over delta x is f prime of x squared. And my delta x at the end turns into a dx. So this is the formula for arc length. That's really where it comes from. It comes right out of the Pythagorean identity up here. Pythagorean identity plus some ideas about linear approximations and so on. All right, so our definition, if y equals f of x is continuous on closed AB, then the arc length is given by L equals integral A to B square root of 1 plus dy dx squared, or f prime of x squared dx. All right, let's look at our first example here. Find the circumference of a circle with radius r. And let me get this on the screen a little better. There we go. So I have a circle here with radius r. And it's going to be given by x squared plus y squared equals r squared. Now, one thing I notice about this is the relation that defines the circle is actually not a function, right? It fails the vertical line test. Kind of a strange thing that we learn about and, maybe don't think about too often, that a lot of our kind of nice figures that we think about in geometry actually aren't functions in the strictest sense and in the algebraic sense. So I think what I'm going to do is I'm going to recognize the fact that if I stick to the first quadrant, my circumference is just 4 times this length L. So if I call this L, just the first quadrant length, arc length, then at the end I'll multiply it by 4 to get the circumference to go all the way around. I see that there is symmetry here, so these other three are going to be exactly, these other three quadrants contributions are going to be exactly the same. So I'm going to come over here and just consider the interval 0 to r. That also means, and this is the length that we're looking to find, that also means that I can represent this function a little bit nicer. I can say y equals square root of r squared minus x squared. So my circumference is going to be 4 times integral 0 to r of some stuff, dx. Let me figure out what goes in there. What do I need? I need square root of 1 plus y prime squared. So let's start by computing y prime. We'll square it, we'll add 1, simplify, square root. That's a lot of algebra, but we'll do it, and then we'll plug that into the integral. So I need square root 1 plus y prime squared. I find it easy to forget the squared and the y prime, just because there's so much going on. It's like you take this derivative, you're like, oh, good, I got the derivative, and then you just want to plug it in right away. I find it easy to forget to square it. So just being really careful with that I get all of the pieces that I need, that I make sure to copy everything down correctly. I actually had a Calc 3 student pop in office hours on Friday and was going through a problem, and she's like, wait, I think you made a mistake there. I don't know. There was, something's not right, not matching up quite right. And it turned out that I just literally forgot to copy a square from one part of the problem to the next. Like I just missed the superscript 2 and that threw everything off. So super easy mistake to make. So let's make sure that we get all of our details correct. So let's do y prime first. So I have y is a function of x. It's the square root of a function of x. That's going to give me 1/2 root stuff. Times the derivative of stuff. Well, the derivative is going to be a negative 2x. The 2's are going to go away. So I get just a negative x on top. So square root of stuff differentiates to 1/2 root stuff times the derivative of the inside is a negative 2x. So we get a negative x left over. The 2's go away. Y prime squared is x squared over r squared minus x squared. I need 1 plus y prime squared. Well, that's 1 plus x squared over r squared minus x squared. Or that is r squared minus x squared plus x squared over r squared minus x squared. My x squareds go away in the numerator. This gives me r squared over r squared minus x squared. Okay. And finally, I need the square root of that. So that's r over root r squared minus x squared. So just taking my time doing it, one piece at a time, working inside out. That's what I need to put in my integral over here. This whole square root bit, the entire integrand, is r over square root of r squared minus x squared. Okay. I've got down to an integral. It's not a terrible looking integral. You can probably imagine that if you just pick kind of like a random function and try to do this, take the derivative, square it, add 1, square root it, most of the time it's going to look pretty terrible. Most of the time we're not going to be able to compute arc length explicitly. We'll be reliant on some kind of approximate technique. But here, works out to be not so terrible of an integral, right? In terms of maybe Calc 1 integrals or integrals you would have seen in Calc 1, it's a pretty terrible integral. But in terms of, what we've seen now that we've worked through some different integration techniques, not too bad. I note this square root of r squared minus x squared. I don't see a simple substitution or something like that that's going to help me out here. So I'm going to jump to a trig substitution. I think x equal r sine theta is what I'm looking for. Why is that? Well, r squared minus r squared sine theta or r squared sine squared theta, is r squared times 1 minus sine squared theta, r squared cos squared theta. That's going to give me an r cos theta on the bottom. Oh, maybe not write that quite so close. So I'm going to have an r over, the denominator is going to be an r cos theta. And as I mentioned before, really tempting to just write kind of d theta here and be on our way, but be really careful. Dx is what? It's going to be r cos theta d theta. These go away. Oh, and I'm jumping the gun still. I need to figure out my bounds. X equals 0 when, well, when sine theta equals 0 or when theta equals 0. And x equals r, well, that's when r sine theta equals r, or when sine theta equals 1, or when theta is pi over 2. Okay, so now that we've got that handled, my r cos thetas divide out. I've got 4r integral d theta. Well, that's just the interval width that I'm integrating over, pi over 2, or that is 2 pi r, which hopefully we recognize as the circumference of a circle. 2 pi times the radius, or 2r is the diameter, pi times the diameter. So for me to walk all the way around the circle of radius r, it would take 2 pi r units of distance that I would have to walk around. Any questions on this one? Okay, let's look at this next example. Find the length of the curve y equals natural log of cosine of x for x in 0 to pi over 4. You might get the feeling that some of these problems, or many of them, have to be carefully constructed. You know, this is a pretty wonky function. I have to be kind of carefully constructed in order to be solvable by hand. So, you know, log of cosine of x, everybody's favorite and most frequently used function, obviously. Okay, but if y equals log cos x, let's figure out what our integrand has got to be. Let's come off to the side here. I need y prime. Log of stuff differentiates to 1 over stuff times the derivative of stuff. So derivative of cosine is negative sine. I need y prime squared. Well, this is obviously negative tan x. Y prime squared is tan squared x. 1 plus y prime squared. 1 plus tan squared x. That's secant squared x. And square root of 1 plus y prime squared is secant x. Okay, so our arc length then is going to be integral 0 to pi over 4 secant x dx. There are two ways we could approach this. One, we could actually get an exact answer here. So I think integral of secant is something like log of secant plus tangent. I don't remember off the top of my head, but it's actually one of the, it's part of one of the longer integrals that is in one of the supplemental videos. So, or we could lean on our previous work and say this is approximately equal to 0.88 0.8814 using an approximate integration technique. So we could use, Riemann sums or midpoint rule or trapezoid rule, or use the built-in functions in our calculator, get about 0.8814 is the answer. But kind of as an exercise, what is the exact answer? It should be approximately 0.8814, so you can check your work. But can we find an exact answer for this? And as I mentioned, the integral of secant of x is a problem that we had done in a previous supplemental video. So you can kind of review that or check that out, or but try to work through it by hand. If you did watch that video, see if you can remember how to construct things so that you end up able to compute the integral. If you if you want to use a table or something or look in the book to check your answer, that's certainly fine. But that's another good integration exercise. As a side note, I don't think this wouldn't be like a fair problem for me to say put on an exam, just like what's the indefinite integral of secant x dx, and expect you to do it by hand, having never seen it before, having no access to a table, and having never seen the trick before. The trick has to do with secant as 1 over cosine, and then you kind of make the one kind of into like a sine squared plus cos squared, and do some strange stuff from there, and it turns out to work out pretty nicely in the end. But it's kind of an intermediate step that you're like, where did that idea come from? And as far as I can tell, the idea just comes from the idea that it happens to work. It really is, at least to my knowledge, in the realm of what I would call a trick, not really a fundamental understanding thing. But see if you can come up with the exact answer for this one. Okay, and let's look at our last example for today. So find the length of the curve, y minus 1 all cubed equals x squared for x in 0 to 8. All right. So if I draw a picture of this, when x is 0, y minus 1 cubed has to be 0, so y has to be 1. When x is 8, y minus 1 cubed is 64. 8 squared is 64. And the cube root of 64 is 4. 4 times 4 is 16 times 4 is 64. I almost said 16, but that's whatever. It's something like the 2/3 power of it. So cube root of 64 is 4, and then we add 1. So y equals 5. And it looks something like this. Right, I see that y looks like x to the 2/3 plus 1. So it's going to look kind of like a square root-ish function. Looks something like that. And again, I want to find L, the length of this curve, as measured along the curve, going from 0, 1 to 8, 5. So that's my goal. Okay, so let's take a look at this. So what could I do? I can see that y is 1 plus x to the 2/3. Take the cube root of both sides, add 1. And let me bring down my formula from up here just so we remember what it is. If we remember that it's basically the Pythagorean identity, it makes it a lot easier to remember, but let's just pop it up here for reference. So what do I need to do? I need to do y prime 2/3 x to the minus 1/3, or maybe I'll call this 2/3 cube root x. What's y prime squared? I square this, I get 4/9 x to the minus 2/3, or that's 4/9 cube root x squared. I'm just reminding myself that I can write this two different ways depending on my preference. What's 1 plus y prime squared? 1 plus 4/9 x to the minus 2/3. And I'm starting to look at this and say, I don't know how nicely this is going to work out, right? It does turn out that I can do this. I did this integral in my notes. I can integrate x going from 0 to 8, square root of 1 plus 4/9 x to the minus 2/3 dx. It does work. It's quite a pain. I need to get a common denominator here. So I would get a x to the 2/3 on the bottom, and then I'd have an 9x to the 2/3 plus 4 all over 9x to the 2/3. What did I do? I did a u substitution with 9x to the 2/3 plus 4. du worked out kind of okay. It wasn't super terrible, but it was a pretty messy substitution, and there were a lot of details that could easily go wrong. So if you want some practice on technique with details, you might actually try to proceed with this as an exercise and see if you can get the answer. The answer is 1/27 times 40 to the 3 halves minus 8. Lots of details, and a little hint is that the u substitution is u equals, what was it, 9x to the 2/3 plus 4. That was the u substitution that I used. Be careful to change your bounds when you change into the u integral. Be careful that your du, that you've got everything right with signs and powers and all of that. So if you want some exercise on, or yeah, if you want an exercise that really lets you practice and drill the nitty-gritty details, which for some problems you can't avoid, this is a good exercise for that. But we could take a different approach. We're just looking for this length, right? The same way that if we were just looking for area, I mean, area is going to be the same area, whether we view it this way or kind of with our head tilted 90 degrees. Same with length. I'm just looking for this geometric idea. What's the length of this curve? Could I instead look at this the other direction? Could I instead look at x equals y minus 1 to the 3 halves? What would that do up here? If I swap the roles of x and y, then my arc length should be, here we're integrating from x equals a to b. Let's say we integrate from y equals c to d, the associated y values to these x values. Square root of 1 plus dx by dy squared, taking x as the dependent variable, y as the independent variable, dy. Is there any reason this shouldn't work? Well, no. I mean, everything about the definition, everything about the construction and everything was perfectly symmetric in x and y. I just chose to factor out a delta x here. I could have just as easily factored out a delta y. There's no reason that one should work and the other should not. So what is dx by dy? And here we have to be extra careful because it just looks so strange. But my independent variable is y. So I differentiate and I get 3 halves, y minus 1 to the 1 half, times d by dy of the inside y minus 1, but that's just 1, so no big deal there. What's dx by dy squared? Well, that's 9/4 times this thing squared, but that's just y minus 1. The square root of y minus 1 squared is just y minus 1. What is 1 plus dx by dy squared? That is 1 plus 9/4 y minus 9/4. That is 9/4 y. And what is this? 4/4 minus 9/4 is minus 5/4. And then what is the square root of all of this? That's, I suppose, 1/2 square root of 9y minus 5. Well, that's my entire integrand. But hey, I can integrate this. I mean, if I needed to, I could use just the u substitution. This is a simple integral to do, at least relatively speaking, relative to how messy this other one would be. Right. Simple is always relative. In Calc 2, simple means a very different thing than in Math 90. So here my arc length I can get by integrating from y equals, let me be careful here, it's not 0 to 5, it's 1 to 5. 1 to 5. 1/2 square root of 9y minus 5 dy. So this is going to be 1/2. I have stuff to the 1/2 power. I integrate, I add 1 to the power. 9y minus 5 to the 3/2 power. I divide by 3/2 or multiply by 2/3. I need to make an adjustment for the inside, so let me do that. If I differentiate this right-hand side, I get 3/2 stuff to the 1/2. The 3/2 cancels the 2/3. I have the 1/2 factor in front left over, and I have a 1/2 power. But then I get a times 9 that comes out from the chain rule. I need an over 9 to deal with that. Or if I wanted to, I could use a careful u substitution and, not do this kind of guess and check method. Going from y equals 1 to 5. So my 1/2 and my 2 cancel. I have a 1 over 27. That takes care of all my factors. And then I have evaluated at y equals 5. I have 9 times 5 is 45 minus 5 is 40 to the 3/2 minus 9y minus 5 evaluated at y equals 1 is 9 minus 5, or that's 4 to the 3/2. That is square root of 4 cubed, that is 2 cubed, or simply 8. I get the same answer either way, but I would much rather do this integral than do this integral. The challenge over here is that I ended up with this wonky x to the minus 2/3 term underneath the square root. Over here, I still ended up with a square root, but the thing under it was just the y to the first term. I can deal with that much more easily. Like I said, it's not impractical to do things in terms of x. It's just lots of messy details, and you have to be really careful. But if you want an exercise where you can have a chance to work on that kind of bookkeeping, keeping all those details straight, just work on the underlying algebra, this is a good exercise for that. You might pull your hair out a little bit. You might have to go back and redo some things a couple of times or check your work, but you should end up with exactly the same answer. And hint, this is the u substitution that you can use. All right, let me stop the recording.